Uh, all right. So good day to everyone, and welcome to the sixth problem solving session on CH20 course. So we'll be starting today, as discussed in the previous live session. We'd first cover the non-dimensionalization parts of the Navier-Stokes equations. We discussed what they are the previous day. The second part that we'd be covering is one problem, a transient problem that has not yet been discussed in the live session. The third part would be the integral solution to the boundary layer problem. We'd also discuss the modeling of a nuclear fuel element right there. And then maybe something about the viscous heat source. So, all right, so let's start. Just give me a moment. All right, so the equations of change that we had discussed earlier look something like this when we talked about the continuity equation for an incompressible flow. It looks something like this. That is the zero vector, and the Navier-Stokes equations were written as something like this. Yeah, so let us just revise all these terms that are involved right here. So v vector is a velocity field that is composed of the u and v and maybe z as well. So respective components of the velocity in the x and y and the z direction. And this entire thing becomes zero because actually it was written something like this: del rho over del t plus grad divergence of rho v vector would be equal to zero. But for a steady state problem, this goes to zero. And for an incompressible flow, this comes out and this entire thing becomes zero. So the second part would be, and this is inherently an equation in two variables, because this v vector is composed of something like this: vxi plus vyj plus maybe vz k maybe. Yeah. So three equations, three variables, and this becomes the mass density of the problem. This is the gradient of the pressure. P is where P is the scalar quantity, the usual normal pressure, and mu is the dynamic viscosity of the fluid, and this del squared, that is obviously the Laplacian. Now, one thing is that you might have seen and modeled a lot of fluid systems. So by the term fluid systems, I would mean something like maybe a channel flow, where you are pushing fluid through the inlet and you're receiving fluid through the outlet, and this entire thing would be something like this, maybe this part. And so anything that involves fluids, and you are and wherever you're trying to model some physical problem using the Navier-Stokes equations, that would comprise of a fluid system. And using the Navier-Stokes equations and different problems, if you remember, the last problem that we encountered was something like this: flow through a channel. And in this flow through a channel, you had to somewhat do this, that, for example, your coordinate system starts right here. Then what you'd be doing is at y equals to 0, you introduce a new null-side boundary condition where you use the x component of the velocity field. And at y equals to, let's call this distance as b, yeah. And at y equals to b, u is again 0, which is the null-side boundary condition, assuming that both of these plates themselves are Vp equals to 0 for both of them. Both of these plates are at rest, and the flow is basically pressure driven. That is, P1 is greater than P2, and the fluid flows from the left side to the right side. So these types of problems are something. Now imagine that you have y equals to b here, and sometimes when the channel is bigger, then you might be having y equals to 0 right here and y equals to b prime right here. But the boundary conditions are same on both these ends. Now, so what you could do is perhaps standardize your entire methodology, your entire formulation of a particular fluid flow problem into a common paradigm. So introducing this common paradigm that helps you to solve different types of fluid flow problems would obviously mean that you need to go beyond this, where you need to be concerned about the depth of the channel, that is the distance between the two plates where fluid is flowing, for a typical example like this one. Or you might be having, for example, if it's a pressure-driven flow, then you might be having to do something with where you are standardizing this part P1 minus P2, so that all problems have a common P1 minus P2. Not literally, because P1 minus P2 would be different for different problems. But if there is a certain possibility to convert everything into standardized, a normalized form, that would mean that we would have a single set of Navier-Stokes equations to solve a multitude of problems. So this is why, and this entire exercise of converting different forms of the Navier-Stokes equations for different problems into one standardized form that can be used for huge diversity of problems is called something as non-dimensionalization. So what do you do in non-dimensionalization is something like this. You try to convert the variables that have dimensions within them into variables that do not have dimensions within them. For example, you have u, which has a dimension of lt minus 1, where L is length and T is time. That gives you meter per second in the SI system. So lt minus 1, you'd like to convert it into something that is of the dimension 1, that has no dimension, that is L O T O M O, something like that. All right, so how to do that is quite it depends on the problem, to be honest, but there is a standard method that you could choose for any problem. So how to do this part can be explained right here. Yeah, so we define something called, so yeah, okay. So we define something that is, let me switch on my video again. It was flickering a lot. Yeah, it's much better now. Yeah. So there was something that is, called characteristic. Characteristic dimension. For example, in the case of length, you could have a certain L naught, that is the characteristic dimension for length. And this could be in either the X or Y or Z, anything, it does not matter. Or you could also have a characteristic, this one is length, and you could have a characteristic velocity, that is U naught. Or further, you could have a characteristic, pressure that could be defined as P1 minus P2 divided by rho times U naught squared, right? Now, how did this come? P1 minus P2, assuming that both of these are in pressures. So the unit of pressure is Pascal. And how's Pascal defined? That is force per unit area. And how's force defined? That is mass times acceleration and divided by area again. So that is m LT minus 2 L2 L squared. And this gives out mL minus 1 T minus 2. That is your unit for pressure. Now, this part is mass density. That is m L inverse cube. So this is for volume, 1 upon volume, and this is for the mass. And in the case of U naught, this becomes L2 T minus 2, L squared T minus T inverse square, because time comes in the denominator. Now multiply both of them, and you get mL minus 1 T minus 2. So obviously, rho times U naught squared can be used to divide P1 minus P2, that is delta P, the pressure difference, to obtain a dimensionless quantity called the non-dimensional pressure. That is also sometimes referred to as P star, which becomes del P over rho U naught squared. Similarly, a non-dimensional length scale can be defined. For example, you could say X star would be equal to, or let's use tilde, right? Wait, this entire thing is freezing somehow. I'm not sure why that's happening. So I'll just close this one. Sorry for all this interruption, but all this technical stuff sometimes takes a toll on me. Anyway, so let's assume that this is P tilde and this is P1 minus P2 over rho u naught squared, which is equal to delta P over rho u naught squared. And you've got x tilde, which is the non-dimensional form of the x coordinate as x over L naught, where L naught is the characteristic length, and y tilde, which is the non-dimensional form of the y coordinate, is y over L naught. So this is how you define all those things. And u tilde can also be defined as u over u naught, where u naught is the characteristic velocity. V tilde would be defined as v over u naught. And are we missing something now? Hopefully not. Yes. So the time term is also missing. So we have this t tilde that is a non-dimensional form of time would be something like t by t naught, where t naught is the characteristic time scale of this entire name formulation, and which can further be written as, L naught or U naught. So obviously, time can be represented as the length divided by the speed or velocity. So L naught by U naught, and this U naught goes up, it becomes T U naught over L naught. Now let's try to replace everything in the Navier-Stokes equations that reads as yeah, this one. Okay. So this reads as, yes, like this, dv over dt would be equal to grad of b in the negative plus mu times grad squared of v vector. Yeah. Okay. Yeah, perfect. So for an ease of understanding, now just another thing that I'd like to do real quick is that how to handle now, rho is done. Rho is already, something like rho does not need to be dimensionalized, non-dimensionalized, and v vector is a velocity field. We already have the non-dimensional forms of the velocity, because v vector tilde would simply be equal to v over u naught in the vector form. In the vector form, yes, and t we already have, and this grad. How to handle this grad and this the Laplacian operator. So you could write del equals to something like del by del x, x cap plus del by del y cap plus del by del z of z cap. And x and y and z are already known in their non-dimensional forms. So this would become del equals, this x can be written as L naught x tilde. To just write it like that, and this would become then del of L naught x tilde. And this L naught will come outside. So this becomes del maybe tilde, yeah, like this. Interesting, right? So using this, and now this del squared would be del 2 over del x squared plus dot dot dot. So del squared would be equal to 1 over L squared, L naught here, del tilde squared. This is how it goes. All right. So this becomes like this. Yes, but that's perfect. Anyway, so now we can start our exercise, because this would become something like d of v vector times L naught tilde, of course. No, maybe, yeah, this one. Let's do this. Sometimes it behaves really something like really wacky. It's really ridiculous. It's not even rubbing something. Okay, forget about it. Just write it like this. Rho times d of times u naught divided by d times L naught by u naught, or representing t in the form of t tilde would be equal to something like this, and this becomes grad becomes 1 over L naught grad tilde, and p would become, going from p to p tilde would give you something like uh, rho u naught squared times p prime. Now you know how this part happens is that you are writing something like del p over del x cap plus dot dot dot, and this is uh, precisely what you mean by delta p in the limit tends to 0. So this becomes del p. And that is how this is happening. So from the del x part, you are getting this L naught. From the del p part, you'll be getting rho u naught squared. So this is how this happens. And this becomes this. And again, that thing becomes something like mhm. Yeah, so this becomes something like rho no, mu times divided by uh excuse me, L naught squared, and from v you've got u naught, and here you have v tilde, and L naught squared, and you've got here del squared right here. So yes, so here you don't have anything like del v or something, because del v is simply non-dimensionalized like with u naught. So this becomes your entirety. So this becomes the entire equation right here. And from here, you can obtain this part. You write it as rho u naught squared by L naught dv over dt. That is the total materials derivative of your velocity field. And this becomes L naught grad of b. So these are not vectors. Just be mindful of this fact that these are just tilde, simple representations. This has not got nothing to do with vectors. And here you got L naught squared the Laplacian of vector. So this is how the non-dimensionalized form of your entire equation looks like. Now, you already see pretty much that a lot of things are canceling from both the sides. You can divide everything by rho u naught square. You can divide everything by rho u naught, So this would yield u naught by L. Or why not? Why is you first divide everything by rho u naught square L naught. Let's do it in one go. So this becomes dv vector over dt tilde. This is the vector sign right here, and this entire thing vanishes right away. Plus we got mu here, 1 excess of u naught right here, and since you're dividing it by L naught, and here you've got L squared. Here you go. And since there is an extra row right here, so it looks like something like this. Okay, so this pretty much looks perfect, right? So this becomes now you need to notice that this is something that we obtain after our exercise, and this has the dimensions of LT M L minus 3, U naught would be LT minus 1, and L naught would be L, and divide everything by mu. So how do you obtain the dimension of mu? So mu can be written, it's quite simple in the sense that mu del u by del x is of the order of, the tau, the shear stress, maybe xy, let's call it. And this is, since this is stress and pressure is also a normal form of the stress, here you have shear stress. So the dimensions of both these quantities are the same. So this should be ml minus 1 t minus 2. And this would be lt minus 1. And this is L. So this entirety goes there. So mu is effectively ml minus 1 t minus 1. Okay, so substitute this entire thing right here, ml minus 1 t minus 1. And what do you observe is something that has laid down the foundations of fluid mechanics in all its entirety. So this entire thing becomes zero, the zero dimension. Or to write it more formally, you could write it something like MOLOTO. Anyway, something's happening to my hand, so this becomes MLOTO. And of course, the other 4 dimensions of that of pressure, temperature, luminosity, and all those things are already have 0 powers. So since those are not relevant to the discussion right here, I'm not mentioning them explicitly. Yeah, so this number, this entire thing, that this non-dimensional group, whatever you want to say, you're free to say it. This entire thing is called the Reynolds number, or abbreviated as RE. All right. So then the final form of the Navier-Stokes equations becomes negative of non-dimensional gradient of B, non-dimensional, and this is 1 over RE, the Laplacian non-dimensional force of the vector. Yes, this is also the non-dimensional form. So this is how the non-dimensional form of the Navier-Stokes equations look like. And yes, so now you see that quite an interesting conclusion right here. For example, if the Reynolds number is very, very high, or net, or maybe let's not write about infinity, but okay, so this is troubling me so much that I guess I need to switch to another window. Don't need this, we don't need this, we also don't need this. Yes, so let's write it like this. The final form of Navier-Stokes equations will look something like this: dt prime equals to minus of. Okay, so I guess the earlier PDF was loaded so much that it stopped responding in its entirety, and this is RE, and this is something like grad squared. That is the Laplacian of V vector, non-dimensional, of course. All right. So let's draw some insight from this relationship. For example, if RE is much greater than 1. So now all of these groups are non-dimensional in nature, so their magnitude can be approximated to 1, right? I mean, not 1, but some factor of 1. So this could be 100, this could be 2000, but all of these, have a magnitude that is an entirely scalar, a non-dimensional number without any dimensions. So if you had to scale something like V, then you'd say that it's harder. Yes, it might be something near to, or maybe twice or thrice or 4 times, or maybe 1/4, or of significant, or something very insignificant percentage of the characteristic velocity, but it would be something of which has a factor of u naught. So similarly, when something scales as 1, so you could always write it could be whatever, it does not matter. It could be 2, it could be 3, it could be 4, but it is not carrying any dimensions, and that is the point that we want to emphasize here. So if RE is much greater than 1, then these terms right here compared to these terms would be much greater. That is, for a Reynolds number that is much greater than 1, this entire term is insignificant compared to the pressure gradient. All right. So this means that the viscous effects could be temporarily neglected. So this reduces the form of the Navier-Stokes equations, like something like this, minus the grad P. So we see that the flow is entirely pressure driven, and these viscous terms are pretty much neglected. So this is what happens during turbulence. For very high Mach numbers, the entire thing is driven by pressure, and that's why it takes a form of a pressure wave. And for RE much less than 1, you could multiply everything by RE. That is a highly viscous fluid. So this term dominates both of these other terms. So effectively, this entire equation becomes something like this, right? Okay, give me a moment. I'll creep up all that stuff that I was writing earlier. Yes. So yes, turbulence and also in viscid fluids. And yes, so effectively, RE conveys us a meaning uh, that effectively indicates the relative magnitudes of the inertial and the viscous forces. So why is this called inertial? You know, inertia is something that is carried by a body that is either at rest or moving. So if it's moving, then it involves the influence of some terms like U, V, W, that is Vx, Vy, and Vz. So effectively, these terms are governing the inertia forces, and that is why this is called inertial term. And this is obviously viscosity because it already contains this viscous term that is mu, that is the dynamic viscosity of the fluid. So that's that. All right, so now that this part is covered, we are now ready to go to another part, another really interesting application uh, of viscosity, okay? And this is flow between plates where one plate is suddenly moved. So let's form a physical intuition of the problem. This is your domain. And what is happening right here is that this part is, let's say, fixed. Or we could be more graceful in our representation and we could just write something like this. That is yes, this is, let's say this is a surface, and this is obviously v equals to 0. And this is a movable plate. Let's color this real quick. And this is suddenly imparted a velocity. Let's call this y. Let's call this x. No way does this represent, so just know that this is infinite. The plate is of infinite length. The surface is of infinite length. So there are no inlet effects considered in this problem. So this is suddenly imparted. Uh, this is suddenly imparted a velocity of v naught, let's say. Yes, at t equals to 0. So at t equals to 0 minus, the entire system is at rest. At t equals to 0, the lower plate is moved at a constant speed of v naught. Now we need to find out the behavior for t greater than 0. Behavior of what? Behavior of the fluid system, the fluid engineering problem that we have right here. We need to model it and we need to find how it behaves for all times greater than 0. So how do we solve this is something now that in earlier problems, in earlier Navier-Stokes equations that we solved, the shell balances, the momentum balances that we conducted, we always assume that the steady state terms are 0. But in this case, can we assume that? No, we are unable to assume that part because this is not a steady state problem, but a transient problem. A transient problem is a problem that involves dependence of your variables on time. That could be spatial variables or that could be your physical variables or anything. Okay, so let's write it something like this. Okay, so let's look at this, the Navier-Stokes equations, b equal to minus of rad of b. This is b plus square b vector non-dimensional form, 1 over Larry. Now, let's call the distance between these two plates as L naught. All right. Okay. Yeah. Now, what we are assuming that this L naught tends to infinity. Okay. So effectively, what is happening is that this lower plate is pulled in the horizontal direction at t equals to 0. This would imply what would happen right here, at this point, we've got the no-slip boundary condition, assuming it to be has some normal surface. So it's not something like it's hydrophobic or super hydrophobic that it will repel the water molecules near to the surface, fluid molecules near the surface, and that would make the no-slip condition invalid, but it's just a general surface that's so that the molecules of the fluid are sticking to this plate. And since they're sticking to this plate due to their viscosity, what would happen that this plate will be dragging all these molecules along with it. And this would effectively translate into a motion, into a linear motion of the entire layer of fluid that sticks to this plate. And this layer of fluid uh, would have a certain influence on the next layer of fluid. But this influence would be weaker because this entire stress that is being transmitted into the shear stress that is being used to move these fluid layers would be completely, the effects would be difficult to observe very far away from the plate. So this is why the effects will keep on decreasing, but there will be certain effects even at infinity. So what would happen? The velocity would be the highest at this descent, and it would keep decreasing, keep decreasing, keep decreasing, until at infinity it becomes 0. So this is how the situation looks. Okay, so all of the previous layer is driving the successive layer. So this is basically shear driven flow. Okay, so this is similar to the Couette flow part, but the difference is that in the Couette flow you had a finite domain of a certain thickness, maybe h, but here you have an infinite domain, and due to this domain being infinite, it would take for something like t tends to infinity to transmit the effect of this dragging plate to the surface, because the traveling time, because every passing instant, the other layer, the previous layer, is communicating to the next layer that now you gotta move, buddy. So, and so subsequently this process keeps on happening for each of these layers. So this effectively implies that the time it takes to reach the surface would be dependent on L naught, and since L naught is infinity, the time would also be infinite. Okay, so there are 3 parts to this problem. So the first thing is you write the initial condition, whatever you have, we got to write that first. Okay. Yes. Mm, Yes, the initial condition can be written as t less than equal to 0 would be, for t less than equal to 0, you have u equals to 0, right? So now what we are doing is, in the x direction you have u, and in the y direction you have v. So it is easy to observe that v equals 0, right? Yes. The reason, the reason being that there are no forces, no effects in the y direction. So that is why you can assume that v is identically 0. Let's write it as identical. And from this part, you can write del u by del x from the continuity equation. Del v by del y would be equal to 0. So del u over del x is equal to 0. This would imply that u is a function of y and t only, because this entire space is defined in 3 coordinates that are x, y, and t. There's no z here, so this is the space and this is the time. So we can write it like this, and the boundary conditions can be written as, for y equals to 0, you have u equals to v naught, and the second boundary condition for y reaching infinity, u reaches 0. Right? Because the closer it is to the surface due to the sticking property, due to the viscosity effects, the no-set boundary condition is valid right here for a general surface, and that would imply that the velocity should be 0 at the surfaces. And once you have this, let us now move on to the Navier-Stokes equation. So this can be written as del v tilde over del t tilde, yeah, plus u vector. We're just expanding it for a better clarity on what's going on inside. U vector del u over del y plus, let's write it. Okay, so let's write it as v vector right here. And UV vector. W is for the z coordinate, but since that's 0, let's neglect it for now. Okay. Now this is effectively 2 equations uh, in a single system of representation. Now we already know that we are having v identically equal to 0 for all x comma y comma t. What this would imply that this entire equation can be reduced into a single equation, because what is this? This is effectively del u over del u tilde over del t tilde x cap plus del v tilde over del t tilde y cap. So when v is 0, the y components, all of the y components vanish. So this entire thing can be written as del u over del t plus u del u over del x plus v del u over del y. We already know that this is 0 from the continuity equation, and since v is 0, this is also 0. So on the left-hand side, you've only got this term remaining. On the right-hand side, you've got something like this. And, since this, we are considering the flow to be one-dimensional. Okay, so, I mean, since v is identically equal to 0, and we are not assuming any gravity right here, G is not there. So this would imply that the entirety of the pressure is constant right here. And this can also be proved like this. So this the y direction. Let's write the y direction Navier-Stokes equations first. So this would give you the left hand side is 0. We already discussed the reasons. Would be something like minus del over del y tilde b tilde plus del tilde squared. That is the Laplacian, and you've got v tilde here. And since v tilde is 0, this becomes 0. So effectively, del p tilde over del y tilde would be equal to 0. This implies that p tilde is a strict function of x and t tilde, which would further imply that p vector is, and yeah. So, but now we are assuming that in the p direction, we don't have anything. In the x direction, we don't have anything. So this is identical equal to 0. So this would imply that both of these terms are 0. So p is not spatially varying. Okay. So this part becomes 0 again. So this entire thing reduces to del u over del t would be equal to, if you expand the Laplacian del squared, then you would get something like RE. The Laplacian can be written as like this one. For the u part, it can be written in del x squared plus del y squared times u tilde. And we are assuming that this thing does not vary with x. U does not vary with x. So if u at x equals to 0 is equal to v naught, then it is v naught everywhere at every point. And if it is something like v naught by 2, then it is v naught by 2 at every point. So this is the intuition behind our analysis. So with x, this u is not varying. It's not a vector. So effectively, this translates this entire equation into something like this: u tilde, t tilde, u tilde, yeah, del y tilde squared. Okay. Now, there is one thing that we can do here to simplify the problem. Del u tilde over del t tilde is del t over L naught V naught. So T divided by T naught, that in T naught is L naught by V naught. So this is V naught here and L naught here. Can be written like this is 1 over RE, and RE is effectively, let's say V naught times L naught. Yeah. Divided, and here you've got this. Okay. And you also change this. So this is okay. Nothing but just some mathematical manipulations to ease our problem. Or let's forget this entire thing. Let's go by what we have right here. Okay. So what this would yield then is, for example, if we consider, let's say dimension, a dimensional term of like. Mhm. I can do it something. Uh, Actually, the target is to remove this RE from this formulation so that we've got a more uh, concise interpretation of, because what is the challenge here? You need to understand that U vector is a function of, let's say, y tilde and t tilde. So if we are able to have an expression among y tilde and t tilde that make this u vector an entire function of something eta, a combination of eta, then that would help converting this entire equation into an ordinary differential equation, which can further be solved using some convenient techniques. Now for that, so the thing is, once you want to combine both of these, equations, so first let us maybe try, since both of us, so first let us try a combination. So we need to unlock the dimensions first, now if we want to try a combination between y prime and t prime, y tilde and t tilde, then obviously they're already dimensionless, so there is no need to convert them into a specific combination that is dimensional. So what we need to do is unlock the dimensions of this equation. And how would you do that? That can be done something like this. Now u tilde is already a dimensionless number, so we won't be touching that at the moment. Just replace this t would be t times divided by L naught times V naught. And this y would be y over L naught. Okay, so this becomes del of u tilde over del t V naught, and L naught comes up. 1 over RE can be written as V naught L naught divided by nu, that is the kinematic viscosity. Well, it was originally, mu V naught L naught divided by rho, and mu by rho is rho V naught L naught divided by mu, and mu by rho is effectively kinematic viscosity, that is mu, or momentum diffusivity as you call that, u prime divided by, this becomes something like L naught squared y prime L naught negative squared del y squared. Yeah, this seems perfect. Okay, so now this thing becomes del u vector by del t L naught by V naught be equal to nu times L naught is becoming something like V naught right here, and L naught comes up del 2u prime over del y squared. This goes to 0, this cancels out. So this becomes del u tilde over del t is nu times del 2u tilde over del y squared. Now, the combined variable eta that we were discussing about can be something like this. Y over some combination of nu and t, so that this entire thing is only dependent on eta. Is that possible? Can you think about it? It is possible, right? Because, nu is mu over rho. What was mu? It was m L minus 1, t minus 2, t minus 1, t minus 1, yes, divided by m L minus 3. Okay, and this becomes L2 t minus 1. So if we multiply it by t, that is the time, then this would yield L squared. And if we take a square root, then this would yield L, which is identical to Y. So that is the philosophy behind choosing this particular combination as the dimensionless group for solving this problem. So let's call this eta. So then we could write del U over del T is equal to del U tilde over del R du tilde over d eta. Now, because this using this would convert u tilde from being a function of y tilde and t to u tilde being a function of only eta. And you multiply this by del eta over del t. So this is something like u prime d by d eta. And this term would become, so this is y over root of nu to the minus 2 minus 1 over 2 t times root of d. So combine these terms. You can probably see that these terms can be combined quite conveniently. So this would become 1 over 2t du by d eta. And write another eta here. Okay, this sounds good. And another part is still 2u over del y squared. And you can write it something like this, del over del y, del u over del y. Okay, so first we write del y as du vector over d eta, del eta over del y, which is 1 over square root of nu t u vector prime, where prime represents d by d eta. So now del over del y of del y u tilde would be d of del y u prime d eta times del eta over del y. And this is 1 over y of eta u prime eta, like this. And this becomes eta over y u prime tilde. Del eta over del y is 1 over nu t squared, of course. And the interesting thing here is that you've got something like this. Del y over del eta is del eta over del y is this. And in the end, just give me a moment. Okay. Yeah, okay. Yeah, okay, so this is going to be a bit complicated if we do it like this. So maybe we could proceed like this, del over del y of 1 over nu t u tilde prime. And that would become, since for when partially differentiating this with y, nu t would be constant. So this becomes u tilde prime by del y. Okay, and this is easy to calculate, right? Because this is something you can write it as del u prime over d eta, del eta over del y. This would become u tilde double prime, and this is 1 over nu t. This is also 1 over nu t. Okay, so now consider the original equation right here. Substituting all these things into the original equation, you can easily obtain something like this, minus eta over twice of t u tilde prime, which is equal to nu times the double y partial derivative of u tilde, that is this, and multiplied by nu, you got 1 over t u double prime. Okay, seems good. So this entire thing becomes cancel t, because this equation is valid for t equals greater than 0. So you can write del u tilde over eta squared plus 1 over 2 eta du over eta. Now, this is really easy to solve. I'll give you just 1 minute to think if you could remember. I'm sure you might have heard of solving these types of equations, but the form is a bit different. So you could try to remember how to solve these types of equations, and then we will discuss it really quick. Okay, don't look at the screen. So I'll be doing my own work so that we don't lose much precious time. Okay, time's up. I hope you were able to do something, find something meaningful out of this. So here we've got, if you take eta as 0, then use u tilde is 1. Okay, so this would mean 1 equals to k1 integral something to something from 0 to 0. Whatever that is, this will be 0, and k2 equals to 1. So this becomes k2 equals to 1. This is the first uh, this is the first constant k2, and for eta tends to infinity, u vector is k1 integration from 0 to infinity e to the power minus e to the square root of 4 d eta plus 1. Oh, and here it is 0. So k1 is equal to minus 1 over uh, integral 0 to infinity e to the power minus e to the square root of 4 d eta. Here we've got k1 as well. Substitute both of these into the original equation, you get k1 is 1, this becomes minus integral 0 to eta, e to the power minus e to the square root of 4 d eta over 0 to infinity, e to the power minus e to the square root of 4 again, d eta. And let's look at the curve of e to the power minus x, for example. This looks something like this. Now imagine if this x was squared. So this means this x will always be positive for the first thing. And if x is always positive, then this thing would become, this part is something like this. So even when you are giving a negative x, it would become positive after being squared. And if this is 1, this is minus 1, this is 1. So beyond 1, this will decrease very sharply. And before 1, it would, it would definitely increase, but the rate would not be as sharp as this one because it is, it's 0.1 squared would be 0.01. So it would be probably more than this one, something more like this, but it will obviously converge to, 0. Yeah. So if it is something like this, then it would be something like close to this, and then this would, yeah. Anyway, so this would be the nature of this curve. And interestingly, from 0 to eta, this is eta. So this area divided by this entire area. So this is what is written right here. And this is written as the error function complement of eta. This is a notation. This is just a minute. Okay, so this is quite, in all basic calculus courses, they teach that this can be obtained as root of pi over 2. So this entire thing becomes a root of 2 over pi. And integral of eta, e to the power minus eta square root of 4 d eta. And this could be written as the error function in terms of eta. This is the formulation of the error function, the proportional area between the integration from 0 to eta to the entire integration in the positive domain. So this is effectively u over V naught is equal to 1 minus erf eta. So U is effectively V naught times 1 minus erf of y over root of nu t. So this is the final answer. All right. So this is how we solved this type of problem that was transient in nature. Now, I would leave the physical analysis and understanding of the intuition behind the problem to you. But obviously, we could just sketch a quick plot right here with U, F, and eta. So it is evident that it would be going something like this. So you see, as eta increases, that is for now, eta increases. Okay, we can do it ourselves. Eta increases could mean two things. One, y increases, and the other, that t decreases, assuming nu constant. Okay. So if y increases, this would imply that you are going further and further away from the moving plate. And of course, the effects of the moving plate would be felt less in comparison to the previous layers, so u vector would be less. And that is exactly what's happening here. And for lesser time, that means it is quite close to the initial, the time instant is quite close to t equals to 0, or maybe not quite close, but as you keep decreasing, it goes close to t equals to 0, and at t equals to 0 is the instant where you've got that impulse on the lower plate. So as t decreases, you'd be having something that the effects are more pronounced for t. The effects are less pronounced for decreasing t, uh, because the effect is not permeating. If for a very for just after moving this plate, the effects would take some time to reach into the further layers. So that would mean that u vector will again decrease from here. So this was a bit of analysis that you could always do. And the next problem that we'd be taking is something like, okay, so we already did this. And then you've got integral solution to the boundary layer problem. Okay, so maybe we do not have much time today, so we pick some other problems compared to, let me check out the question for once. Yes, right. This is much better. Yeah. Okay, so let me describe the problem to you. Mhm. There we go, yeah. Okay, or we could do two problems, yes. Just switch to. Okay, so everybody must have heard about electrical wires, right? Uh, Let's draw a wire. Let's assume that this is the copper wire twisted, multiple strands twisted into one, and there is a certain insulation right here. Okay, so since this is carrying a current, let's say I, so this wire element, this copper element is producing heat at the rate of I squared R, where R is the resistance of this wire. Okay, now this I squared R is the rate of heat produced. So integrate this with respect to time and this would give you the total heat loss. So assuming, all of this excess energy that is getting that is being generated, excess thermal energy that is being generated due to the current is emanated as heat. So we could effectively call this problem of a constant heat source, assuming I is constant and R is constant, a constant electrical heat source within another conducting material. Okay. So now, okay. Mm-hmm. Now, what we want to model is this part, this wire, the metal part. We are not concerned about the insulation part. Let's call this radius to be R, and you've got a uniform current I flowing right through the wire. So you could write this SE or SC. Let's call this. This is the volumetric heat generation. So this can be written as I squared. Divide this by I squared times R, that is rho L over A. And if you want, this is through the entire wire with a length of L. If you want a linear heat source rate, then you could write it as SC by L would be equal to I squared. And you got let's talk in terms of conductivity, then that's sigma. And this is A. Okay. So, just adjust these expressions to obtain something like this. Let's call this I squared divided by sigma, or sigma, let's call it sigma star. And the respective units of this is not current now, no. I star, let's write this like this. So, and this unit is ampere per, let's call this meter squared. And this is ohm inverse and meter inverse. So you can work out the units by yourself, and you'd be able to get this, that this is basically in watts per meter cube, something like that. Okay. So now we want to perform an energy balance in this entire wire. For example, this is the wire. This is a solid surface, entire thing is solid. And from the center, we take an element like this. Of a thickness. Let's take the thickness as delta R. And let's take this radius as R. This overall radius is capital R. Just to differentiate the small bit, the capitals. Okay. Yeah, right there. And now what we could do is look at this boundary element really carefully. This is just a magnified image of this wall. This is del R. And this is R. So what's happening here is, assume that the rate of heat transfer right here is QR. So the rate of heat transfer from this part would be QR plus delta R. Let's call this del R. Okay. And and let us assume that this entire length is L. So what we could write is at R, the rate of heat rate across. So what since this is our control volume, we will be writing, flux in minus flux out. Our flux in equals to flux out, or let's write it in terms of quantity. Quantity in is equal to quantity out plus quantity generated plus quantity stored. Since there is no storage right here, we close this to 0. And the inside quantity, if we assume that Q is the unit watt per meter square, for example, the heat flux, then you need to multiply it by the curved surface area to obtain. So this is what's happening here. Let me just, so everywhere it is QR, 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 QR right here, QR right here. This interval has QR. Watt per meter square, the flux, the heat flux. So this becomes 2 by RL times QR at R would be equal to 2 by R LQR at R plus delta R. Excuse me. And this is, let's say, SC, for example. This, let's assume that this is volumetric heat generation, and we also write a dot here for further clarification that it is a rated entity, that is per unit time. So quantity generated would be multiplied by the entire volume of the control volume, which is the element's volume, which is, pi 2 pi, or just a minute, pi times r plus del r squared minus r squared, and multiply it by L. This is the volume of the element. And this can further be exemplified as 2 r del r times L, because del r squared would be insignificant compared to, r's, compared to this part, and r squared gets cancelled. Looks like there was some problem. Anyway. So now this entire thing becomes, let's take out 2 pi r common, rq r at r plus del r minus rq r at r would be equal to minus sc dot 2 pi l r del r. All right, so cross this out, because L naught equals to 0, y naught equals to 0. We can cross this out conveniently, and this is RQR, R plus del R, minus RQR at R divided by del R would be equal to minus R times SC dot. And this just looks like d by dr of RQR for limit delta R tends to 0 is equal to R SC dot. And the final thing that could be written as, d by dr of RQR, or we could just solve it. Since SC dot is constant, you could write it as something like RQR would be equal to minus R squared SC dot by 2 plus C1. Some constants even, yes. Write it divided further by 2 plus C1 over R. Now, we use our identical logic that we used in one of our earlier problems, that, QR is the heat flux through at any certain radius, at any section of this entire wire. So QR can never be infinite. No, an infinite heat flux would mean an infinite energy, which is impossible. So this would mean that for QR to be finite at R equals to 0, you need to have C1 identically equal to 0. So this would imply that QR is equal to minus R times SC dot over 2. And since this entire medium, this entire wire is at rest, U at R equals to 0, this would imply that the heat that the heat flux has contributions only from heat conduction. There is no advection involved right here. So if we only have heat conduction in the system, we can always write that QR is something like K as K dt over dr. And this is identical equal to R SC dot by 2. So this becomes and T becomes now you need some boundary condition. For example, if you know if you could measure the virus temperature at the surface, let's say this temperature is T naught, then you could just write R at R equals to R, you've got T equals to T naught, and this would have C2 equals to R squared SC dot by 4K, and then T would be equal to SC dot by 4K times R squared minus R squared. For SC dot equals to constant, of course. So this entire problem is now well defined, you know. T naught, T naught here. Okay. Well, I hope you can take a look. You took a look since I was waiting at this moment. So now let's switch to another problem. This is an identical problem, you know. Just let me. The tabs are shuffling randomly. I'm not sure why that's. Just a moment.